All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So let's just draw the shear moment diagrams for our compound beam that we have here. That compound beam just means we can find everything, treating it like a frame. We have two members that are pinned together. Also, we have a pin at A, a fixed support at E. Technically, we don't have enough equilibrium equations to also get the X components in here. That doesn't matter for us, though, because we're looking at shear moment, so it's only straight up and down, and moments from that. We'd be able to say that AX equals EX, and that's all the farther we really need to go. We'll ignore those pieces. But if we were to try to find our free body diagram of the entire thing, I would have, even ignoring the X components, AY, EY, and ME. The X equations, we can't count because we're ignoring those. I'd have three unknowns there and two equations I could work with. I can't solve that out using statics. This is statically indeterminate. Instead, I have to explode this and treat it like a frame. So I could look at AC and CE, and ignoring the X pieces, I'd have AY, CY equal and opposite because I'm moving from one member to the next, and at E are fixed support and EY and an ME. Again, technically there's AX and EX, they just don't matter for our problem. We lose one equation, we can just take them out. But let's come in and try to work with that. If I'm trying to make a shear moment diagram, I need these support reactions. So we explode this and we treat it like a frame so I can find my support reactions. So let's come and look at that. Again, I can do two equations per thing in here because I have already used my X equation to say AX equals EX or AX equals CX and CX equals EX. Same idea in there. We have forces in the Y and moments. They're really all I can work with in here. If I go to CDE first, I'd have CY, EY, ME. Three unknowns, I have two remaining equations. I need to go to AC. I'd have AY and CY. Two unknowns, I have two equations. I can go there. So we're going to start with, remember, ABC. So if I'm looking at A, B, C, we have our free body diagram drawn out, and I can just come in and say, well, let's find moments. If we do moments at A, I can find CY. So with positive, going counterclockwise, summing my moments about point A is going to get me, well, CY will cause a counterclockwise rotation. We're working with the top free body diagram here. So it's going counterclockwise about A, and it's 10 feet away. It is 10 plus 5, 15 feet away. So 15 CY. And then we'll get the rest on the next line. But our distributed load is going to cause a clockwise rotation. So subtract it out. Minus area will be 10 times 500. 10 times 500. That's our force. We need distance in there. From A to the centroid of our rectangle is just the middle of a rectangle. So halfway in will be half of 10 times 5. And that should get us to 0. If I solve for CY, I'm going to get that CY is 1,666 pounds, and we're going up. But because that's that internal connection here, we want to say on which member. That's up on ABC. And the reason that matters for us is because technically it's also going down on our next member. We could report it that way as well. CY is 1,666 pounds going straight down on CDE. On CDE. Both of these statements are true. Newton's laws tell us we have to go equal and opposite as we bounce from one member to the next. So we're just applying that rule in there. But with CY known, I can find AY. If I just sum up my forces in the Y direction. Summing forces in the Y. I'm going to get, well, I have AY going up. AY. I have my distributed load coming down, so minus the area. 10 times 500. And CY is going up, plus 1,666. Gets us to 0. Which if I solve that, I get AY. I'll get a positive number, so I guess the right direction here. It is going up, and it is 3,333 pounds going straight up. From there, we can move on and say, well, I can look at member CDE to figure out my other sports. With C known, I know it's really going down on CDE. I have EY and ME, two unknowns to go in there. So let's go to my next piece on CDE, and we can work with this one. Let's just start out, and some forces in the y will get me my EY. Summing forces in the y direction. I have CY comes down, so we'll start there. CY is negative 1666. I have 1,200 coming down, minus 1,200. And I have EY going up, plus EY should get us to 0. Which if I solve that for EY, I'm going to get here that EY is 2867, 2,867 pounds going up. And finally, I can figure out my moment, that MA, my fixed support resist moment. Don't leave this one off there. But with positive, going counterclockwise, I can sum my moments up about any point. Let's do them at point E. Summing my moments about point E is going to get me, I have a clockwise moment. I assumed it was clockwise. So negative ME, that variable I'm actually finding in here. My CY will cause a counterclockwise rotation. So plus CY we know is 1666. 1666 force times my distance all the way here is 5 plus 5, 10. Times 10. And my 1,200 will cause a counterclockwise rotation. So plus force is 1,200 times my distance is just 5. And that should get us to 0. Which if I solve that for ME, I'll get a positive, which means I assume the correct direction here. Clockwise. ME is going clockwise. And it is a pretty big number. 22,667 pound-feet going clockwise. That gets us enough. I can start my shear moment diagrams. Again, we got to get those support reactions. If it's a compound beam, we're going to have to break it up into pieces that we can treat like a frame. But if I'm doing my shear moment diagram, I could try to come up with 1, 2, 3, 4 sets of equations, or I could come in and do the area method. It's going to be way easier to do the area method. So let's tackle that. I need to get my area for any distributed load. Let's call that area 1. Area 1 is a rectangle. It's just going to get us, the area is base times height. 10 times 500. 10 times 500. This is 5,000 pounds equals 5,000 pounds. And that's everything I need to make my shear diagram. So we'll come in and we start at the left edge, work left to right, and apply all the rules that we have written up here. But if I start at the origin, we'll put a dot at the origin. And as I start to move over, I hit AY and the distributed load. We always do that concentrated force first because it's applied in an infinitely small area. So it will push us up by AY. AY is, we found it, 3333. So we'll go from 0 and immediately we jump up, straight up to 33 pounds. From there, we can start moving across. And we know our shear, applying this rule, our shear at the end of an area, shear at the end of area 1 equals the shear at the start of it, 3333 minus area 1. So 3333 minus 5,000 is going to get us to negative 1667. Negative 1,667. I had a constant for my distributed load, which means I should have a linear function for my shear. I can just connect my dots in here, straight down. This is going to end up being in the way, so I'm going to move it over. Negative 1667. From B to C, I go straight over because I had no distributed load, so I am constant. And at C, what do we get? We have CY going up and CY going down. We could think of this as two different ways. Technically, this should close it out. We could treat each half of this as its own little beam in here. Negative 1667 plus CY would get us to 0. And then we're immediately starting a new beam from C to E. And we start with CY 1667 going straight back down. Really, we have an infinitely small distance where we go up and back down. Up to 0, back down. that makes no difference. On our overall free body diagram, we could also say we wouldn't be including C in here. If we are looking at the overall free body diagram, there's nothing we have to deal with at this point, and we can just keep going straight over. Either way, whether we think of that as two beams and each one closes out and starts and ends at 0 and immediately changes away for the new beam, or our overall, we do the same thing here. We can get to where our 1200 is applied. It'll make us immediately go down. We drop down from 1667 minus 1,200 would be negative 2867, which is our EY value. So at E, we've gone constant over because there's no distributed load. We go from negative 2867 up, getting us back to 0. And that means we have started and ended our diagram here at 0 for everything, which is a good sign for us. We should always have that happening with our shear moment diagrams. From there, we can come on and say, well, let's figure out our shear moment or our moment half. To do that, I need to figure out where this is 0 at. That 0 shear should correlate to a max or a min moment point. So let's come in and dimension out some pieces here. We're coming down. We can go from the axis over two distances in here, x1 and x2. And I'll need those to get areas figured out. So let's do proportional triangles in here. My ratio of base to height in my first triangle is x1 over 3333. That should be x2 over 1667, which should be equal to my total x distance, 10 feet, divided by my total change in height, which is going to be that area. Area 1 was 5,000, which we could also get by just adding those two together. But solving that, x1 over 33 equals 10 over 5,000. We're going to get the x1 is 6.67 feet. And similarly, x2 over 1667 equals 10 over 5,000. x2 is 3.33 feet. And the easy check is those two do add up to 10. So we're on the right track with this. But from there, I need a couple more areas. We already used 1, so let's start at 2. So our triangle here is area 2. The next triangle, 3. We'll make this 2 areas because there is a pin in the middle of that. We'll talk through what's going on there. But area 4, area 4, area 5, and area 6. So let's find all of these. Area 2 is our triangle. Area 2 should be equal to 1/2. Our base is x1, 6.67, times our height, 3333. Times 3333. Is going to get us that we have, this is equal to, area 2 is 1111, or 111 pound feet. And I'm going to have to write small to get everything else in here, but we can work with this. Our next one, area 4, we can say is, not area 4, 3 comes after 4. Area 3, also a triangle, is 1/2. Our base is x2, 3.33, times our height, negative 1667. Or this is going to get us, area 3 is negative 2778 pound feet. Area 4 should be, area 4 and area 5 are actually going to be equal to each other. They're both 5 feet wide. Our height is negative 1667. So let's just do those in one line. Area 4 equals area 5, which should get us to, our base is negative 5, and our height is negative 1667. Or this is going to get us, I combined them in my notes into one thing, but so we'll write this just divided by 2. This is 16,667 over 2, and we can work with that. Pound feet. And one last area to get. We need area 6. Should get us, we're a rectangle, so our base is 5. 5 times our height is negative 2867. Or this is going to get us to negative 14,333 pound feet. And we can work with our areas then to find our moment diagram. So we'll start at 0 and just work left to right. Put our dot here at the origin. As we start coming in here, there's no couple moment here. There's the far right edge, so we'll have to count for it there. But as I come in, my moment at the end of area 2 is the moment to start, 0, plus area 2, 11, 111. So I'm going to increase up here to 11, 111. I had a linear function, so I should be parabolic now. And I should be concave down because I was sloping down. So we'll get a parabola that peaks at 11, 111. Then we can say, what about the end of area 3? Well, the moment at the end of an area, we're using this rule here. The moment at the end is the moment to start, 11, 111, plus the area. Area 3 is negative 2778. So 11, 111 minus 2778 should get me to 8,333. 8,333. And we're parabolic there. It's the same parabola as before. It's the same linear slope in there. From there, I can come in and say, well, what about area 4? That should be the moment at area 3 is 8333 plus 1667 divided by 2, which the math there is actually doable. It is 8333 pound feet. Negative because we are going down. Negative for both of them. But so in this area 4, 8333 minus 8333 should get us to 0. And we're linear because we had a constant shear in that region. That should make sense for us. Again, if we think of this as two beams from A, B, C, we should start and end at 0. We're getting back to 0 at the end of this. There's no couple moment right there. Something pushes us immediately away from that. Also, a pin doesn't resist any moment. So logically, right where that internal pin is, we should have 0 moment coming out for that. There's multiple ways we can kind of think through that. But that's always going to be true for us. Anytime we have an internal pin, our moment at the pin is 0. So we could have just made this one area, area 4 and 5. We've gotten 1667 and just straight line straight all the way through. We would have gotten to negative 1667. But we split it up into 2. We should hit 0 right here. But so 8333 minus our next area, 83 or 0 minus 8333 will get us, continuing our straight line on, down here to negative 8333. Which should be our next piece that we need to work with. From there, there's one more area to get, area 6. Our moment at the end of that, at the right edge of our beam, should be negative 8333 minus 1433, or that's going to drop down, and we're going to get to negative 22,000, negative 22,667, 667. At that point, we do have a couple moment here. Our couple moment we found, ME was 22,667. Going clockwise. Clockwise always increases our moment. So we're going to jump straight back up to 0. And we can shade in our entire moment. Don't get thrown off just because it's a compound beam. That internal pin here isn't going to ultimately, it will be necessary to do that to find our support reactions. But it doesn't do anything to our shear diagram. And our moment diagram, it doesn't do anything there, but it always gives us a 0 point right at that point. Again, we could just think of this as two individual beams that we have smushed our diagrams together to complete in there. We can do compound beams. If we can do a normal shear moment diagram, and we can do straightforward frame problems. We can get through these. But hopefully this was useful. If it was, stick around, watch more videos, hit that like and subscribe button. Let's get you an A with JJ.